And now in this lecture we'll answer on two questions. In the first question, we'll find out the area of this circle that is inside square ABCD. And in the second question, we'll find out the value of the green area that is inside a quarter circle. So we'll start with the first question. In the drawing, we have square ABCD. Inside square ABCD, we have a circle. We know that angle CBT, this angle equals to 30 degrees. We also know that line segment PD equals to 5 units. And our mission is to find out the area of this circle. Okay, so first of all, we define the center of this circle as O. And we will join points O and P together by a straight line. Point O is the center of the circle, point P is the point of the circle itself. Therefore, OP is the radius of this circle that we will define as R. And we have here the radius OP that is drawn to the point of tendency. That is to say, it is drawn to point P, that is the point of tendency of tangent AD with this circle. And therefore, according to rule number 1, tangent AD will be perpendicular to the radius PO. That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, we'll join points O and Q together by a straight line. Point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is the radius of the circle that is equal to R. And again, we have the radius OQ that is drawn to the point of tendency. Therefore, according to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. This angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. We also know that ABCD is a square, and all the angles inside the square are right angles. So this angle is a right angle. This angle, it is also a right angle. This angle is a right angle. And finally, this angle is a right angle. So inside quadrilateral AQPO, this quadrilateral, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of the fourth angle, in total the four angles inside quadrilateral AQPO In total, they must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So 270 degrees plus this angle, in total they must be equal to 360 degrees. So this angle, the missing angle, must be equal to 90 degrees, because 270 degrees plus 90 degrees is 360 degrees. That is the sum of the angles in any quadrilateral. So in order to complete the sum of the angles in this quadrilateral to 360 degrees, this angle must be equal to 90 degrees. So inside quadrilateral AQPO, we have 4 right angles, and therefore quadrilateral AQPO is a rectangle. Quadrilateral AQPO is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, side AQ must be equal to side PO and rectangle AQPO. So AQ equals to PO. But we have already found out that PO equals to R. So can I write here that PO equals to R? And from this equation, AQ equals to PO equals to R, we will derive that AQ is also equals to R. AQ equals to R. Yeah. AQ equals to R. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that QO equals to AP. QO equals to AP. But we have already found out that QO equals to R. It is the radius of the circle. And for this equation, R equals to QO equals to AP, we will derive that AP is also equals to R. AP equals to R. Yeah, AP equals to R. So we actually found out that quadrilateral AQPO is not a rectangle but a square. Why? Because on the fact that all of its sides are equal to each other, they are equal to R. Therefore, quadrilateral AQPO is a square. So we also know that ABCD is a square, and we know that all the sides of a square are equal to each other. That is to say, side AD equal to side AB. AD equals to AB. In square ABCD, side AD must be equal to side AB, because all the sides in the square are equal to each other. What is the value of side AD? The value of side AD is equal, side AD equals to R plus 5. So we can write here that side AD equals to R plus 5. And what is the value of side AB? Here, side AB, this side is equal to R plus QB. AD equals to R plus QB. So we found out that R plus 5 equals to R plus QB. Here we subtract R from this equation and we get that 5 equals to QB, or QB equals to 5 units. QB equals to 5 units. So we can write down here that QB equals to 5 units. Yeah. This line 7 QB equals to 5 units. In the next step I present to you rule number 2, and we will implement rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. So here we have the common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule number 2, PA equals to PB. We can implement rule number 2 in our drawing. Why? Because in our drawing we focus on the common external point, point B. From the common external point, point B, we have two tangents to this circle, tangent BQ and tangent, the second tangent is tangent BS. And according to rule number 2, they are equal to each other in their lengths. That is to say, tangent BQ equals to tangent BS according to rule number 2. But we have already found out that BQ equals to 5 units. So we can write here that BQ equals to 5 units. And for this equation, 5 equals to BQ equals to BS. We derive that BS is also equals to 5 units. BS equals to 5 units. Here, BS, and 7 BS equals to 5 units. What is the size of this angle, angle QBS? Angle QBS equals to 90 degrees minus 30 degrees. Again, angle QBS equals to 90 degrees minus 30 degrees, that is 60 degrees. In the next step, we join points Q and S together by a straight line. By joining points Q and S together, we created here triangle QBS. This triangle QBS. in triangle QBS, both those two sides are equal to 5 units, therefore they are equal to each other. That is to say, side BS equals to side BQ in triangle QBS. So those two sides are equal to each other, and we have the rule that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides we have those two angles. Therefore, those two angles must be also equal to each other because of the fact that they are located in front of equal sides. So if this angle equals to alpha according to our definition, then this angle must be also equal to alpha because of the fact that those two angles that are located in front of equal sides must be equal to each other. Okay. We know that the sum of the angles in any triangle is 180 degrees. So in triangle QSB, this angle equals to 60 degrees. So the sum of the two other angles must be equal to 180 degrees minus 60 degrees. 180 degrees minus 60 degrees is 120 degrees. That is to say, alpha plus alpha must be equal to 120 degrees. So I write it down. We found out that in triangle QBS, the sum of the two angles alpha plus alpha, in total they must be equal to 120 degrees. Alpha plus alpha is 2 alpha, so 2 alpha equals to 120 degrees. We divide this equation by 2, so alpha equals to 120 degrees over 2, that is 60 degrees. So I found out that angle alpha equals to 60 degrees. So here, this is angle alpha that is equal to 60 degrees. And this angle alpha is also equals to 60 degrees. So in triangle QBS, this triangle we have triangles that are equal to 60 degrees. Therefore, triangle QBS is an equilateral triangle. Triangle QBS is an equilateral triangle because it has three angles that are all equal to 60 degrees. We know that in a equilateral triangle, all the sides must be equal to each other. So, in the equilateral triangle QBS, side QB equals to 5 units, side SB equals to 5 units, therefore the third missing side, side QS, must be also equal to 5 units. Here QS equals also to 5 units. Okay. In the next step, we'll join points O and S together by a straight line. Point O is the center of the circle, point S is the point of the circle itself, therefore OS is the radius of this circle that is equal to R. And we have the radius OS that is drawn to the point of tendency, that is to say the radius OS it is drawn to point S, that is the point of tendency of tangent PT with this circle. Therefore, according to rule number 1, we get that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. In the next step, I will copy quadrilateral OSBQ in a new page and will analyze triangle and quadrilateral OSBQ. Angle OSB, this angle equals to 90 degrees according to rule number 1. So this is quadrilateral QBOS that I copied from the original drawing. We know that the sum of the angles in any quadrilateral is equal to 360 degrees, and especially in this quadrilateral QBOS. So what is the value of the missing angle? The value of the missing angle will be equal to 360 degrees minus the sum of the three other angles. So the value of the missing angle, that is actually angle QOS, angle QOS, this angle will be equal to 360 degrees minus the sum of three other angles, minus the sum of 90 degrees plus 90 degrees plus 60 degrees. So that is to say the missing angle, angle QOS, will be equal to 360 degrees minus 90 degrees plus 90 degrees is 180 degrees, and 180 degrees plus 60 degrees is 240 degrees. So the value of the missing angle is 360 degrees minus 240 degrees, that is 120 degrees. So I found out that this missing angle equals to 120 degrees. Okay, here This missing angle QOS equals to 120 degrees in its size. In the next step, I will present to you the law of cosines, and we will implement the law of cosines in the green triangle QOS. Okay. So what is the law of cosines? The law of cosines is true in any triangle. So if we have triangle ABC that could be any triangle, this is triangle ABC. We know that the length of side AB is A units, the length of side AC is B units, and side BC equals to C units in its length, and the angle between side AB and side AC is theta. Then, according to the law of cosines, in this triangle ABC, we will get that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. I'll repeat again, in this triangle ABC that could be any triangle, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Now we will implement the law of cosines in the green triangle QOS. This green triangle QOS. So I'll copy triangle QOS in a new page, and we will implement the law of cosines in triangle QOS. So this is the green triangle QOS that I copied from the original drawing. Side Q equals to R, side OS equals to R, and side QS equals to 5 units, and angle QOS equals to 120 degrees. According to the law of cosines, we will get that five squared equals to R squared plus R squared minus 2 times R times cosine 120 degrees. I'll repeat again, according to the law of cosines, 5 squared equals to R squared plus R squared minus 2 times R times cosine 120 degrees. Okay. This equation is the implementation of the law of cosines in triangle QoS. 5 squared is 25. It is equal to r squared plus r squared. R squared plus r squared is 2r squared minus 2 times r is minus 2r squared times cosine 120 degrees. Cosine 120 degrees is minus 1/2. So here we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. Minus times minus is plus. So in conclusion, we get that 25 equals to 2r squared plus r squared. 2r squared plus r squared is 3r squared. So in conclusion, we found out that 25 equals to 3r squared. Here we will divide this equation by 3, and we will get that r squared equals to 25 over 3. R squared equals to 25 over 3. We know that the area of any circle, the formula for the area of any circle is pi r squared. So the area of our circle is pi r squared. But we have already found out that r squared equals to 25 over 3. Therefore, we can substitute r squared in this formula by 25 over 3. So the area of our circle will be equal to pi times r squared. And r squared is 25 over 3. So in conclusion, we found out that the area of our circle is 25 pi over 3 square units, or in terms of numbers, it is equal to 26.18 square units. I'll repeat again. We found out that the area that we are looking for, the area of this circle, equals to either 25 pi over 3 square units, or in terms of numbers, it is equal to 26.18 square units. So we finish with the first question. In the next step, I will present to you the second question, and we will solve the second question in 3 different methods. So, in the drawing, we have a quarter circle. Inside this quarter circle, we have a small circle. We know that line segment CD equals to 8 units. We also know that this angle ACD equals to 90 degrees. And our mission is to find out the value of the green area. Okay, so we'll start with the first method, and we'll define the center of the small circle as J. We'll define the point of tendency CD with the small circle as E. We'll define the point of tendency OB with the small circle as F. We'll join points J and D together by a straight line. Point J is the center of the small circle, point E is the point of the small circle itself, therefore EJ is the radius of the small circle that we will define as R. And here we have the radius EJ that is drawn to the point of tendency, therefore this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. We will join points J and F together by a straight line. Point J is the center of the circle, point F is the point of the circle itself, therefore JF is the radius of the circle that is equal to R. And we have the radius JF that is drawn to the point of tendency, therefore according to rule number 1, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. We know that AOB is a quarter circle, therefore point O is the center of the quarter circle, and this angle is equal to 90 degrees. We also know that because of the fact that AOB is a quarter circle, AO must be the radius of the quarter circle that we define as capital R. So we know that AO equals to capital R, it is the radius of the quarter circle. So AO as a radius of a quarter circle, it is absolutely a straight line. So if we focus on this side of the straight line AO at point C, here the sum of the angles must be equal to 180 degrees, according to rule number 3, that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at this side of the straight line AO at point C? We have this angle that is equal to 90 degrees, plus the missing angle. In total, they must be equal to 180 degrees. Therefore, the missing angle must be also equal to 90 degrees in order to complete the sum of the angles on this side of the straight line AO at point C to 180 degrees. This angle must be equal to 90 degrees. Okay. In the next step, from point J, that is the center of the small circle, we will draw perpendicular on CO. Again, from point J, we will draw perpendicular on CO. So here, this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point J and CO as T. In quadrilateral CETJ, this small quadrilateral, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So the fourth angle must be also equal to 90 degrees in order to complete the sum of the angles in the small quadrilateral to 360 degrees. The missing angle must be equal to 90 degrees. Likewise, in the lower quadrilateral TJOF, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. Therefore, the fourth angle must be also equal to 90 degrees. So we found out that angle EJF, this angle equals to 90 degrees plus 90 degrees, that is 180 degrees. So angle EJF equals to 180 degrees, and therefore angle EJF is a straight line. Because it equals to 180 degrees. If angle EJF is a straight line, then line segment EJF is a straight line. And if line segment EJF is a straight line, then EF is also a straight line. Line segment EF is also a straight line. So if EF is a straight line, it means that quadrilateral CEOF is a rectangle. Quadrilateral CEOF is a rectangle because it has 4 right angles. Okay, and we know that the opposite sides of a rectangle are equal to each other. That is to say, CO equals to EF in rectangle CEOF. CO equals to EF. CO equals to EF in rectangle CEOF. But we have already found out that EF equals to R plus R, that is 2R. So we can write here that EF equals to 2R. And for this equation, CO equals to EF equals to 2R, we will derive that CO is also equals to 2R. CO equals to 2R. Okay, CO equals to 2R. In the next step, we'll join points D and O together by a straight line. Point O is the center of the quarter circle, point D is the point of the quarter circle itself, therefore CO is the radius of the quarter circle, that is equal to capital R. In the next step, we will implement the Pythagoras theorem on the right green triangle, triangle COD. So, on the right green triangle, triangle COD, by PT is the relation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse on the right green triangle, triangle COD is OD. Therefore, the square of the hypotenuse is OD square. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to CO square plus CD square. I'll repeat again. In the right green triangle, triangle COD, according to the Pythagoras theorem, OD square equals to CO square plus CD square. OD equals to capital R, therefore OD square is capital R square. That is equal to CO square. CO equals to 2R, therefore CO square is 2R square, that is 4R square, plus CD square. CD equals to 8 units according to what is given as the equation, therefore CD square is 8 square, that is 64. In conclusion, we found out that according to equation number 1, capital R square equals to 4R square plus 64. Here we subtract 4R square from this equation, equation number 1. And we get that according to equation number 1, capital R square minus 4R square equals to 64. Found out that according to equation number 1, capital R square minus 4R square equals to 64. But what is actually the area of the green shape? For the drawings it's very easy to see that the area of the green shape equals to the area of the quarter circle minus the area of the small circle. I repeat again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. So the area of the green shape equals to the area of the quarter circle. What is the area of the quarter circle? The area of the quarter circle equals to the area of the circle that is pi times capital R square over 4. So the area of the quarter circle equals to pi times capital R square over 4 minus the area of the small circle. The area of the small circle equals to pi R square. So in conclusion, we found out that the area of the green shape equals to pi times capital R square over 4 minus pi R square. Here we take pi over 4 as a common factor out of those two expressions. So pi over 4 is a common factor. What is left from pi times capital R square over 4 after we took from it pi over 4 as a common factor? What is left is actually capital R square. And what is left from minus pi R square after we took from it pi over 4 as a common factor? What is left is actually minus 4R square. Why? Because minus 4R square times pi over 4 equals to minus pi R square. So in conclusion, we found out that the area of the green shape equals to pi over 4 times capital R square minus 4R square. But this expression, capital R square minus 4R square, equals to 64. Therefore, we can substitute capital R square minus 4R square by 64. So we'll do it now, and we'll get that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16. So this expression in total equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. Okay. So finished in the first method. In the next step, I will present to you how to find out the area of this green shape according to the second method. In the second method, we'll use all the things that we have already found out in the first method. We have already found out that in the first method that CO equals to 2R, AO is the radius of the quarter circle that is equal to capital R. We have already found out that this angle equals to 90 degrees according to rule number 3 in the first method. This is the radius of the small circle. This is also the radius of the small circle. This angle equals to 90 degrees. Point O is the center of the quarter circle. In the next step, we complete the quarter circle to a circle. So we completed the quarter circle to a circle. We'll extend the radius AO by straight line until it intersects with the circle. We define the intersection point of the extended radius AO and the circle as T. We will extend the straight line DC by straight line until it intersects with the circle. We define the intersection point of the extended straight line DC and the circle as point M. We will join points O and M together by a straight line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the big circle that is equal to capital R. We join points O and D together by a straight line. Point O is the center of the big circle, point D is the point of the circle itself, therefore OD is the radius of the big circle that is equal to capital R. We extended the straight line DC by a straight line, and when you extend the straight line by a straight line, the result must be a straight line. So the result, that is DM, must be also a straight line. So DM is a straight line. If we focus on the lower side of the straight line DM at point C, here the sum of the angles must be equal to 180 degrees according to rule number 3. So which angles we have at the lower side of MD at point C? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees. Therefore, the missing angle must be also equal to 90 degrees in order to complete the sum of the angles on the lower side of the straight line MD at point C to 180 degrees. This angle, the missing angle, must be equal to 90 degrees. So you have here two right triangles, triangle AMOC and triangle CDO. We'll prove that those two right triangles can go into each other. So we write it down. We'll prove that the right triangle, triangle MCO, is congruent to the right triangle, triangle CDO. So why those two right triangles can go into each other? Why those two right triangles can go into each other? First of all, side CO is a common side that belongs to both triangles, so CO equals to itself. CO equals to CO. It's a common side that belongs to both triangles. In addition, we have MO equals to OD. They are both the radii of the big circle, therefore they are equal to each other. So here we proved that in those two right triangles, the hypotenuse and one perpendicular congruent. Therefore, we actually proved that those two right triangles can go into each other. And I'll explain you why. Because if we have, for example, right triangle ABC, this is the right triangle, triangle ABC. With hypotenuse AC that is 5 units and side AB is equal to 4 units. And we have another right triangle, triangle DEF. This is the right triangle, triangle DEF. With the hypotenuse that is also equal to 5 units and with one side that is equal to 4 units also. So those two right triangles have the hypotenuse and one perpendicular that congruent. Actually, the third missing side in those two right triangles must also congruent. Why? Because according to the Pythagoras theorem, the value of BC will be equal to the square root of 5 units minus the square root of 4 units. 5 square is 25, minus 4 square is 16. 25 minus 16 is 9, and the square root of 9 is 3. Likewise, EF, according to the Pythagoras theorem, will be equal to the square root of 5 square minus 4 square. And that is equal, of course, to also 3. So we actually found out that if we have two right triangles with the hypotenuse and one perpendicular that congruent, then the third side must also congruent. Here, in those two right triangles, the hypotenuse and the perpendicular congruent. Therefore, the third side of those two right triangles, that is BC in this right triangle and EF in this right triangle, must also converge. Why? Because according to the Pythagoras theorem, the third side in both the right triangles must be equal to 3 units. So we actually proved that the two right triangles, because of the fact that they converge in the hypotenuse and one perpendicular, the first side must also converge. Therefore, the right triangle, triangle MCO, is congruent to the right triangle, triangle COD, according to side rule. Okay? Because if we have the hypotenuse and one perpendicular that congruent, the third side must also congruent. Therefore, those two right triangles congruent to each other according to side rule. And from the fact that they congruent to each other, we will derive that side CD in the right green triangle equals to side CM in the right triangle, triangle CMO. CD equals to CM. CD equals to CM according to the rule that corresponding sides of congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the two corresponding sides, that is to say CD and CM, must be also equal to each other. But it is given as the equation that CD equals to 8 units. Here CD equals to 8 units. And from this equation, 8 equals to CD equals to CM, we derive that CM is also equals to 8 units. CM equals to 8 units. Here, point O is the center of the big circle, point T is the point of the big circle itself, therefore OT is the radius of the big circle, that is equal to capital R. What is the value of line segment AC? The value of line segment AC from the drawing, it is very easy to see that AC equals to AO minus CO. Again, AC equals to AO minus CO. AC equals to AO minus CO. That is to say, AC equals to AO, that is the radius of the big circle, that is equal to capital R, minus CO. CO equals to 2R. So in conclusion, we found out that AC equals to capital R minus 2R. AC equals to capital R minus 2R. In the next step, I will present to you rule number 11, and we'll implement rule number 11 in our drawing. What is rule number 11? Here we have chord AB intersects with chord CD at point O. Again, chord AB intersects with chord CD at point O. So if this is the data that has been given to us, then the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can implement rule number 11 in our drawing. Why? Because in our drawing, we have chord AT intersects with chord MD at point C. I repeat again. In our drawing, we have chord AT intersects with chord MD at point C. Point C is the intersection point of chord AT with chord AD. Therefore, according to rule number 11, we'll get that MC times CD, MC times CD equals to AC times CT. AC times CT. I'll repeat again. Now, drawing, we have chord AT that intersects with chord MD at point C. Therefore, according to rule number 11, we get that MC times CD equals to AC times CT. MC equals to 8 units and CD also equals to 8 units. So MC times CD is 8 times 8, that is 64. That is equal to AC. The value of AC is capital R minus 2R times CT. What is the value of CT? CT is 2R plus capital R. Again, CT is 2R plus capital R. So in conclusion, I found out that according to rule number 11, 64 equals to capital R minus 2R times capital R plus 2R, or 64 equals to capital R plus 2R times capital R minus 2R. Here we have the algebraic identity that A plus B times A minus B equals to A squared minus B squared. We'll use this trigonometric identity in order to find the value of capital R plus 2R times capital R minus 2R. Number specific expression, capital R, A equals to capital R and B equals to 2R. Therefore, this expression, capital R plus 2R times capital R minus 2R equals to, according to this algebraic identity, to A squared minus B squared. A squared, what is the value of A squared? A equals to capital R, therefore A squared is capital R squared minus B squared. B is 2R, therefore minus B squared will be equal to minus 2R squared. Minus 2R squared. So in conclusion, we found out that 64 equals to R squared minus 2R squared. That is to say, we found out that (64) equals to capital R squared minus 2R squared is minus 4R squared. So, in conclusion, we found out that 64 equals to capital R minus 4R squared. But here we have already found out that capital R squared here we have so we found out that 64 equals to capital R square minus 4R square. Okay. And what is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. I'll repeat again. The area of the green shape equals to the area of the quarter circle minus the area of the small circle. And we know that the area of the quarter circle equals to pi times capital R square over 4 minus the area of the small circle. The area of the small circle equals to pi R square. So here we'll take pi over 4 as a common factor out of those two expressions. So inside the brackets we're left only with capital R square minus 4R square as we did in the first method. But what is the value of capital R square minus 4R square? According to what we have already found out, that capital R square minus 4R square equals to 64. Therefore, we can substitute this expression capital R square minus 4R square by 64. We'll do it now. We'll get that in total the value of the green shape equals to pi over 4, and capital R square minus 4R square is 64. So we found out that the area of the green shape equals to 64 over 4 is 16. So in total this expression equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. We finished with the second method. Next step, I'll present to you how to find out the area of the green shape according to the third method. So here we have already found out in the first method that CO equals to 2R. We know that AO is the radius of the quarter circle that is equal to capital R. We have already found out in the second method that AC equals to capital R minus 2R, and we have already found out that this angle equals to 90 degrees according to rule number 3. This is the radius of the small circle. This is also the radius of the small circle. That is R. In the next step, we complete a quarter circle to a semicircle. We'll extend the radius AO until it intersects with the semicircle. We'll define the intersection point with the extended radius AO in the semicircle as M. Point O is the center of the big circle, of the quarter circle. Point M is the point on the semicircle itself. Therefore, OM is the radius of the semicircle that is equal to capital R. So here we extended the radius AO by a straight line. AO is a radius is a straight line, and when you extend a straight line by a straight line, the result is a straight line. So we know that AM is a straight line that is equal to 2R, to 2 times capital R, and it passes through the center of the semicircle, that is to say from point O. So we can see AM as a chord that passes through the center of the semicircle. Any chord that passes through the center of the circle or semicircle must be the diameter of the semicircle or the circle. So AM, chord AM that passes through the center of the semicircle, that is to say from point O, must be the diameter of the semicircle. So AM is the diameter of the semicircle. Because of the fact that it is a straight line that passes through the center of the semicircle. So it is the diameter of the semicircle. Okay, AM is the diameter of the semicircle. In the next step, we join points M and D together by a straight line. We join points A and D together by a straight line. So here we created peripheral angle ADM, and peripheral angle ADM rests on AM, that is the diameter of the semicircle. And we have rule number 5. According to rule number 5, any peripheral angle that rests on the diameter of a circle or a semicircle must be equal to 90 degrees. So here we have peripheral angle AMB that rests on AB, that is the diameter of the circle. Therefore, peripheral angle AMB equals to 90 degrees. We can implement rule number 5 in our drawing. Why? Because in our drawing we have peripheral angle ADM. This peripheral angle ADM rests on AM, that is the diameter of the semicircle. Therefore, according to rule number 5, we get that peripheral angle ADM equals to 90 degrees. And peripheral angle ADM equals to 90 degrees according to rule number 5. We'll focus on the right triangle ADM. On the right triangle ADM, we'll define this angle as alpha. We'll define this angle as beta. So in the right triangle ADM, this angle equals to 90 degrees. So if this angle equals to 90 degrees, the sum of the two other angles in triangle ADM must be equal also to 90 degrees. Why? Because 90 degrees plus 90 degrees is 180 degrees, that is the sum of the angles in any triangle. That is to say, alpha plus beta must be equal to 90 degrees. Alpha plus beta must be equal to 90 degrees. Okay, we subtract alpha from this equation and we get that beta equals to 90 degrees minus alpha. Then we subtract alpha from this equation and we subtract beta from this equation and we get that alpha equals to 90 degrees minus beta. We focus on the right triangle ADC. In this right triangle, this angle equals to beta. This angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees, that is the sum of the angles in any triangle. So this angle must be equal to 90 degrees minus beta. But we have already found out that 90 degrees minus beta equals to alpha, so we can substitute 90 degrees minus beta here by alpha. Likewise, we'll focus on the right triangle CDM. On the right triangle CDM, this angle equals to alpha. This angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus alpha. So this angle equals to 90 degrees minus alpha, but we have already found out that 90 degrees minus alpha equals to beta, so we can substitute this angle 90 degrees minus alpha by beta. In the next step, we'll prove that the right great triangle ADC is similar to the right triangle CDM. Okay, so I write it down. We prove that the right triangle ACD is similar to the right triangle CDM. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to alpha, therefore they are equal to each other. That is to say, angle ADC this angle equals to this angle, this is actually angle CMD. Both angles equal to alpha, therefore they are equal to each other. In addition, both those two angles are equal to beta, therefore they are equal to each other. So this angle is angle CAD, and is equal to this angle, that is angle CDM. Both angles are equal to beta, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, therefore they are equal to each other. So this angle is angle ACD is equal to this angle, that is angle DCM. Both angles are equal to 90 degrees, therefore they are equal to each other. So we actually proved that the right triangle ACD is similar to the right triangle CDM according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that side AC in triangle ACD over side CD in triangle CDM is equal to side CD in triangle ACD over side CM in triangle CDM. I'll repeat again. We conclude that AC over CD equals to CD over CM. Okay. AC equals to capital R minus 2R. CD equals to 8, according to what is given as the question. What is the value of CM? CM equals to 2R plus capital R. So in conclusion, we found out that capital R minus 2R over 8 equals to 8 over capital R plus 2R. Here we'll cross multiply this equation, equation number 1, and we'll get that 8 times 8 is 64, that is equal to capital R plus 2R times capital R minus 2R. We have already found out that capital R plus 2R times capital R minus 2R, we have already found out that it is equal to capital R square minus 4R square. So in conclusion, we found out that according to equation number 1, 64 equals to capital R square minus 4R square. Okay, and what is actually the area of the green shape? We have already found out that the area of the green shape is equal to the area of the quarter circle minus the area of the small circle. Repeat again, we already found out that the area of the green shape equals to the area of the quarter circle minus the area of the small circle. We have already found out that the area of the quarter circle equals to pi times capital R square over 4, and we already found out that the area of the small circle equals to pi R square. Here we took pi over 4 as a common factor out of those two expressions, and found out that inside the brackets we will have capital R square minus 4R square. But this expression, capital R square minus 4R square, equals to 64 according to equation number 1. So you can substitute capital R square minus 4R square by 64. We do it now, we get that pi over 4 and capital R square minus 4R square is 64. So we found out in conclusion that the area of the green shape equals to 64 over 4 is 16. So in total this expression equals to 16 pi. So in conclusion we found out that the area of the green shape according to the third method equals to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. We finished with the second question. In the next step, I'll summarize the lecture and start with the first question, of course. In the drawing, we have square ABCD. Inside square ABCD, we have a circle. We know that this angle CBD equals to 30 degrees, line segment PD equals to 5 units, and our mission is to find out the area of this circle. So we define the center of the circle as O. OP is the radius of this circle that is drawn to the point of tendency, therefore this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule number 1. We have OQ, that is the radius of this circle that is drawn to the point of tendency, therefore this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule number 1. We know that all the angles inside square ABCD are right angles, so those 4 angles are all right angles. So in quadrangle AQPO, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus the size of the fourth angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. So the missing angle must be equal to 90 degrees. In order to complete the sum of the angles in this quadrangle to 360 degrees, this angle must be equal to 90 degrees. So in quadrangle AQPO, we have 4 right angles. Therefore, quadrangle AQPO is a rectangle. We know that the opposite sides of rectangle are equal to each other. That is to say, AQ equals to PO. But we have already found out that PO equals to R. And from this equation, AQ equals to PO equals to R, we will derive that AQ is also equals to R. Here, AQ equals to R. Likewise, according to the sum of the opposite sides of rectangle are equal to each other, we get that AP equals to QO. But QO equals to R. And for this equation, R equals to OQ equals to AP, we will derive that AP equals to R also. Here, AP also equals to R. So we found out that quadrangle AQPO is not a rectangle but a square because of the fact that all of its sides are equal to each other, they are equal to R, that is the radius of this circle. We know that in any square, all the sides of any square are equal to each other. That is to say, in square ABCD, side AD must be equal to side AB. AD equals to AB in square ABCD. What is the value of AD? AD equals to R plus 5. What is the value of AB? AB equals to R plus BQ. So in conclusion, we found out that R plus 5 equals to R plus BQ. We've subtracted R from this equation and found out that BQ equals to 5 units. Here, BQ equals to 5 units. Then I presented to you rule number 2 and we implemented rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have the common external point, point P. From the common external point, point P, we have tangent PA and tangent PB. And according to rule number 2, PA equals to PB. You can implement rule number 2 in our drawing, because in our drawing, we have the common external point, point B. From the common external point, point B, we have tangent BQ and tangent BS. And according to rule number 2, they are equal to each other. That is to say, BQ equals to BS according to rule number 2. But we have already found out that BQ equals to 5. BQ equals to 5. So from this equation, 5 equals to BQ equals to BS, we will derive that BS is also equals to 5 units. BS equals to 5 units. What is the size of this angle? This angle equals to 90 degrees minus 40 degrees, that is 60 degrees. Then we join points Q and S together by a straight line. In triangle BSQ, those two sides are both equal to 5 units, therefore they are equal to each other. And we have the order in front of equal sides in the triangle, they are equal angles. So those two angles that are located in front of equal sides must be equal to each other. So if this angle is alpha, this angle must be also equal to alpha because of the fact that those two angles are equal to each other. So both those two angles are equal to alpha. So in triangle SBQ, this angle equals to 60 degrees. Therefore, the rest other two angles must be equal to, the sum of the rest other two angles must be equal to 180 degrees minus 60 degrees, that is 120 degrees. That is to say, alpha plus alpha must be equal to 120 degrees. Here, alpha plus alpha equals to 120 degrees. Alpha plus alpha is 2 alpha, that is equal to 120 degrees. We divided this equation by 2 and found out that alpha equals to 120 degrees over 2 is 60 degrees. So we found out that those two angles, they are both equal to 60 degrees. Therefore, in triangle SQB, we have three angles that are all equal to 60 degrees. Therefore, triangle SQB is an equilateral triangle. And we know that in equilateral triangle, all the sides are equal to each other. So side SB equals to 5, side BQ equals to 5, and therefore the missing side, side SQ, must be also equal to 5 units. Then we join points O and S together by a straight line. Point O is the center of the circle, point S is the point of the circle itself, therefore OS is the radius of the circle, that is equal to R. We have the radius OS that is 1 to the point of tendency, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. Then I copy triangle quadrangle OSBQ in a new page, and we analyze triangle quadrangle OSBQ. This is quadrangle OSQB that I copied from the original drawing. The sum of the angles in this quadrangle is 360 degrees. Therefore, 360 degrees minus the sum of the three angles must be equal to the size of the missing angle. So that is to say 360 degrees minus 90 degrees plus 90 degrees minus 60 degrees, it is the size of this missing angle. So that is to say 360 degrees minus 240 degrees is 120 degrees. Therefore, the missing angle equals to 120 degrees. So here, this angle equals to 120 degrees. Then I presented to you the law of cosines, and we implemented the law of cosines in the green triangle, triangle QOS. The law of cosines is true in any triangle. So if we have triangle ABC here, that could be any triangle. The length of AB is A, the length of AC is B, and the length of side BC is C, and the angle between side AB and side AC is theta. Then according to the law of cosines, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. We implemented the law of cosines in triangle QOS. In triangle QOS, according to the law of cosines, we get that 5 squared equals to R squared plus R squared minus 2 times R times cosine 120 degrees. 5 squared is 25, R squared plus R squared is 2R squared, minus 2R times R is minus 2R squared, cosine 120 degrees is minus 1 half. we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. Minus times minus is plus. So in conclusion, we found out that 25 equals to 2r squared plus r squared. 2r squared plus r squared is 3r squared. So 25 equals to 3r squared. We divided this equation by 3 and we found out that r squared equals to 25 over 3. So, and we know that the area of any circle is pi r squared. So the area of our specific circle is pi r squared. But we have already found out that r squared equals to 25 over 3. Therefore, we can substitute r squared in this formula by 25 over 3. We did it, and we got that the area of our circle equals to pi times r squared. And r squared is 25 over 3. Therefore, the area of our circle, it will be equal to 25 pi over 3 square units. So in terms of numbers, it is equal to 26.18 square units. We finished with the first question, then I presented to you the second question, and we solved the second question in 3 different methods. In the drawing, we have a quarter circle. Inside the quarter circle, we have small circle. We know that line 7 CD equals to 8 units. Angle ACD equals to 90 degrees. And our mission is to find out the value of the green area. Okay, here we define the center of the small circle as J. JE is the radius that is drawn to the point of tendency. Therefore, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. Likewise, JF is the radius that is drawn to the point of tendency. Therefore, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. This angle equals to 90 degrees because of the fact that AOB is a quarter circle. This angle equals to 90 degrees according to rule number 3. Okay. And AO equals to capital R, that is the radius of the quarter circle, because of the fact that AOB is a quarter circle. Okay. Then from point J we draw perpendicular to CO. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point J and CO is T. So in quadrangle CEJT we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. Likewise in quadrangle TJFO we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So angle EJF, this angle equals to 90 degrees plus 90 degrees, that is 180 degrees. So angle EGF equals to 180 degrees, therefore angle EGF is a straight line. If angle EGF is a straight line, and EJF is also a straight line, and if EJF is a straight line, then line segment EF is also a straight line. So if line segment EF is a straight line, it means that quadrangle CEOF is a rectangle. Why? It is a rectangle because it has 4 right angles. So quadrangle CEOF is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, CO equals to EF. CO equals to EF. But we have already found out that EF equals to R plus R, that is 2R. And from this equation, CO equals to EF equals to 2R, we derive that CO is also equals to 2R. CO equals to 2R. Then we join points O and D together by a straight line. Point O is the center of the quarter circle. Point D is the point of the quarter circle itself, therefore OD is the radius of the quarter circle, that is equal to capital R. Then we implemented the Pythagoras theorem on the right green triangle, triangle COD. According to the Pythagoras theorem, in the right green triangle, triangle COD, D all square equals to C all square plus CD square. Again, D all square equals to C all square plus CD square. CD is the radius, and OD is the radius of the quarter circle that is equal to capital R, therefore OD square will be equal to capital R square. CO is 2R, therefore CO square is 2R, is 2r squared, that is 4r squared. CD is 8, so CD squared is 8 squared, that is 64. So in conclusion, we found out that capital R squared equals to 4r squared plus 64. Here we subtracted 4r squared from this equation number 1. We found out that capital R squared minus 4r squared equals to 64. What is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle itself. The area of the quarter circle will be equal to pi times capital R squared over 4. Pi times capital R squared over 4. And the area of the small circle equals to pi R squared. Here we took pi over 4 as a common factor out of those two expressions. What is left from pi times capital R squared over 4 after we took from it pi over 4 as a common factor? What is left is actually capital R squared. What is left from minus pi R squared after we took from it pi over 4 as a common factor? What is left is actually minus 4 R squared, because minus 4 R squared times pi over 4 is minus pi R squared. But this expression, capital R squared minus 4 R squared, equals to 64. Therefore, we can substitute this expression by 64. We did it when we got that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16, so this expression in total equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. Then I presented to you how to find out the area of this green shape according to the second method. In the second method, use the things that we already found out in the first method. We have already found out that CO equals to 2R in the first method. AO is equal to capital R, it is the radius of the quarter circle. And this angle equals to 90 degrees according to the first method, according to rule number 3 in the first method. This angle equals to 90 degrees because it is a quarter circle AOB. Then we completed the quarter circle to a circle. We extended the radius AO by straight line until it intersects with the circle at point T. We extended the straight line DC by straight line until it intersects with the circle at point M. We joined points O and D together by straight line. Point O is the center of the big circle. Point D is the point of the big circle itself. Therefore, OD is the radius of the big circle that is equal to capital R. Likewise, point O is joint points O and M together by straight line. Point O is the center of the big circle. Point M is the point of the big circle itself. Therefore, OM is the radius of the big circle that is equal to capital R. We extended the straight line DC by straight line. So if you extend the straight line by straight line, the result that is DM must be also a straight line. So DM is a straight line. If you focus on the lower side of the straight line DM at point C, here the sum of the angles must be equal to 180 degrees. So which angles we have here? This angle equals to 90 degrees, therefore the missing angle must be equal also to 90 degrees in order to complete the sum of the angles in the lower side of the straight line DM at point C to 180 degrees. This angle must be equal to 90 degrees. So we have here two right angles, triangle COM and triangle CDO. We prove that those two right angles can go into each other. Again, we prove the right triangle MCO can go into the right triangle CDO. Why they can go into each other? First of all, we have side CO that is a common side that belongs to both triangles. And DO equals to OM, why? Because they are both the radii of the big circle, therefore they are equal to each other. We proved that the hypotenuse and one perpendicular is congruent with those two right triangles. We proved that those two right triangles can go into each other according to side rule. Why? Because, for example, if you have two right triangles here that can go into each other by the hypotenuse and perpendicular, then the third side must be also congruent according to the Pythagoras theorem, because here BC will be equal to the square root of 5 squared minus 4 squared, that is 3. So if we have hypotenuse and perpendicular that congruent in two right triangles, the third side must be also congruent. For that reason, we proved that the two right triangles MCO and COD can go into each other according to side rule. And for the fact that they can go into each other, we derive that CD equals to MC. According to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, CD and MC, must be also equal to each other. But it is given us in the question that CD equals to 8 units. And for this equation, AD equals to CD equals to CM, we will derive that CM is also equals to 8 units. Here CM equals to 8 units. Here, what is the value of AC? AC equals to AO minus CO. So AC equals to AO, that is capital R, minus CO, that is 2R. So in conclusion, found out that AC equals to capital R minus 2R. Point O is the center of the circle, the big circle. Point T is the point of the big circle itself. Therefore, OT is the radius of the big circle, that is equal to capital R. Then I presented to you rule number 11, and we implemented rule number 11 in our drawing. According to rule number 11, if we have chord AB that intercepts with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can implement rule number 11 in our drawing. Why? Because in our drawing, we have chord AT that intercepts with chord AMD at point C. Therefore, according to rule number 11, we get that MC times CD equals to AC times CT. Okay? MC times CD equals to AC times CT. MC times CD is 8 times 8, that is 64. AC is capital R minus 2R. CT is capital R plus 2R. So in conclusion, we found out that 64 equals to capital R minus 2R times capital R plus 2R, according to the algebraic identity A plus B times A minus B equals to A squared minus B squared. We get that this expression equals to capital R squared minus 4R squared, that is equals to 64. So in conclusion, we found out that 64 equals to capital R squared minus 4R squared. What is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. The area of the quarter circle equals to pi times capital R squared over 4 minus the area of the circle, that is pi R squared. We took pi over 4 as a common factor out of those two expressions, so inside the brackets we left only with capital R minus 4R squared. But according to what we already found out, capital R minus 4R squared equals to 64. So we can substitute capital R squared minus 4R squared by 64. We did it, and we got that pi over 4 times 64 equals to the area of the green shape. 64 over 4 is 16, so in total this expression equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. Then I presented to you how to find out the area of the green shape according to the third method. In the third method, we know that CO equals to 2R, and we completed the quarter circle to a semicircle. We extended the radius AO by a straight line, and point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the semicircle that is equal to capital R. Here AM is the diameter of the semicircle. We join points M and M together, we join points A and D together by a straight line. According to rule number 5, verify an angle ADM that rests on the diameter of the circle equals to 90 degrees. We define this angle as alpha, we define this angle as beta. So in the right triangle ADM, we know that alpha plus beta must be equal to 90 degrees. Because this angle equals to 90 degrees, therefore alpha plus beta must be equal to 90 degrees. Therefore beta must be equal to 90 degrees minus alpha, and alpha must be equal to 90 degrees minus beta. We focus on the right triangle, triangle CDM. This angle equals to beta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus beta, but 90 degrees minus beta equals to alpha, so we substitute 90 degrees minus beta by alpha. Then in the right triangle DCM, this angle equals to 90 degrees, this angle equals to alpha, therefore this angle must be equal to 90 degrees minus alpha, but 90 degrees minus alpha equals to beta, so we substitute 90 degrees minus alpha here by beta. Then we prove that those two right triangles can point to each other according to angle, are similar to each other according to angle similarity rule. Why? Those two angles are both equal to alpha, therefore they are equal to each other. Those two angles are both equal to beta, therefore they are equal to each other. Those two angles are both equal to 90 degrees, therefore they are equal to each other. So those two triangles can point to each other according to angle similarity rule. Therefore, from the fact that they can point to each other, we derive that AC over CD equals to CD over CM. AC is capital R minus 2R, CD is 8, and CM is capital R plus 2R. We cross multiply this equation and found out that 64 equals to capital R plus 2R times capital R minus 2R. This expression equals to capital R square minus 4R square. In conclusion, we found out that 64 equals to capital R square minus 4R square. What is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. The area of the quarter circle equals to pi times capital R square over 4. The area of the small circle equals to pi R square. We took pi over 4 as a common factor out of those two expressions, so inside the brackets we left only with capital R square minus 4R square, but capital R square minus 4R square equals to 64. So we substituted capital R square minus 4R square by 64, and found out that the area of the green shape equals to 64 over 4 is 16. So in total this expression equals to 16 pi. So in conclusion, we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. So in all three methods, we found out that the area of this green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. Okay, thank you very much.